Alright, so we will start off with the lecture today from the point where we left off yesterday, and we will look at the continuum model of the Debye layer near charged surfaces. Okay, so the basic physics that we saw yesterday was quite simple in the sense that ions which have same charge as the charges of the wall, they are repelled, whereas ions of opposite charge, they are attracted towards the wall. And apart from having this kind of an attraction, there is also always a persistent thermal motion. And this thermal motion is primarily caused due to the molecular level vibrations or the ionic level vibrations. And the origins of the description of the persistent thermal motion is through tools of statistical mechanics, statistical thermodynamics. In fact, statistical thermodynamics can also help in describing the structure of the Debye layer, but we will not go through that route today. We will look at the continuum modeling and we will make certain assumptions. Okay. So the ions with the same charges, they are called as co-ions, whereas the ions with the opposite charges are called as the counter ions. Now, first of all, we must derive some kind of an expression for the relationship between ionic charge density and the local electric potential. And this relationship has to be very general. It should not be necessarily tied down to the Debye layer that we're trying to study. So we must first establish this. Meaning, if there is a region of high potential, what is the ionic charge density? Similarly, if there is a region of low electric potential, what is the ionic charge density? We must first do this. And so the starting block is to write down an expression for the chemical potential. So the chemical potential for the positive and negative ions is given by a constant plus Kb times T log of C over C naught. So this is the expression for the chemical potential without any electric field, but the potential in the presence of the electric field, the chemical potential, it will have an additional work done because of the potential. So it will be Ze times phi. All right. So what is the how do you identify these terms? So this is, see, chemical potential is always an additive thing. So this is the chemical potential at equilibrium, or not equilibrium, but at STP or NTP conditions. So this is under standard conditions. So the chemical potential mu plus minus will be equal to mu naught when C plus minus or C for plus or minus becomes equal to C naught, that is we are in bulk, or when phi becomes equal to 0, which again means we are in bulk. So the chemical potential mu naught is the potential when the potential of an ion when the ion is in the bulk. Now what about this kBt ln C plus minus over C naught. So let me just move this. So Kb is the Boltzmann constant, and this particular term, it is in case you have if you remember the thermodynamics that you might have learned in your 11th or 12th, this is the log of the activity. So any deviation from the bulk concentration leads to an increase or decrease in the chemical potential depending on what is going on. So this particular term is the activity of the ions, and it is devoid of any kind of it is not tied down to any kind of electric potential. This is solely based on the concentration. Okay. So meaning if you have a bulk with a certain number of density, ion density, so suppose this has a bulk density of 1000 ions per nanometer cubed. So suppose this is the density. So in this density, if you now try to push an extra ion, you have to do some work. You cannot simply take an ion and push it over here. So once you push it in, you have squeezed in one more ion compared to its bulk condition. Originally it was in the bulk condition and everyone was happy. Now you have taken one more ion and you have pushed it. So that penalty is reflected in an increase in the chemical potential. Not going into the derivation of this expression because that goes into physical chemistry and that takes time. Now what about the last term? So the last term, if you recall from electrostatics, so Zd phi is like the work done on a charge to bring it from infinity, right? Do you recall this? It is the work done on a charge to bring it from infinity to a location which has a potential phi. Meaning there is an ion, and why do we say at infinity? Because at infinity there is no potential. We can assume that at infinity the potentials of everything in the universe has died down. So if you bring that charge from infinity to this point which has a certain potential, you have to actually work against that barrier, and that work done is manifested through an increase in or a decrease in the chemical potential depending on the nature of the valency. So Z here represents the valency of ion, meaning that for NaCl, something like NaCl, which dissociates into Na plus and Cl negative, for Na plus the Z will be 1, for Cl negative Z will be equal to -1. It is the valency of the ion. And E is of course the protonic charge. It is the charge magnitude held by a proton. And T is the temperature. And C is the bulk concentration. So the starting point is to describe the chemical potential, and this kind of methodology works well not only in describing this distribution, but in general even for statistical mechanics or statistical thermodynamics, this can be a very valid starting point. And this method is quite general. It's not really just pertaining to the distribution of the ions in the electrical double layer. Okay, so now if we in case we assume that, okay, so first of all, I mean, there are certain assumptions in me writing this. I have implicitly assumed that whatever electrolyte will be there, so I have simply written it as one Z. Ideally, it has to be Z plus E phi and Z minus E phi. Okay, but I have assumed that uh, whatever electrolyte we will have, it will have a symmetry, meaning if there is one positive ion, there will be one negative ion. You can always modify this analysis for the case of multivalent ions. It will not change the heart of the problem. So I have assumed that Z plus is equal to Z and Z minus is equal to minus Z, where now Z is simply a number like 1, 2 and so on. Okay, that is why this plus minus has appeared over here. Okay, so I mean, is it clear what this plus minus means? So this plus minus means if I write down mu plus, that is the chemical potential for the positive ion, it will be this particular expression. And for mu minus, that is the chemical potential of the negative ion, it will be this particular expression. Alright, so now the next idea is, given this chemical potential, the system must come to a thermodynamic equilibrium. So the condition from thermodynamics, in order for a system to be in thermodynamic equilibrium, is that the gradient of chemical potential has to be zero. Now look, I mean, it starts to make sense that the gradient has to be zero, meaning if a system has a distribution of ions so that this region has a larger, so if I call this as mu left and mu right, if mu left has a larger thermodynamic, has a larger chemical potential than mu right, then obviously there is an disequilibrium of the forces acting between them, and so there will be some redistribution of either the ions or the potential in order for this chemical potential to balance out. It is like having a, a tube like this, and initially this tube is closed and this tube is filled with water. The level of water over here is larger, the level of water over here is lower. So you open the tube, and the fact that the left tube has larger water, it means it has a larger gravitation potential. So water has to flow so as to equilibrate the gravitation potential. Similarly, in case the chemical potential is higher, then there must be some kind of a flow, and in this case, instead of flow of water, there will be a redistribution of ions and redistribution of the electric potential so as to render the gradients or the differences in space of the chemical potential equal to zero. So far, whatever I have mentioned, does it make sense, or would you like me to repeat this? Anyone? Am I audible?
Yes, sir, you can go ahead.
Okay.
Yeah.
So let's continue. So the gradient of the chemical potential has to be zero. So let's see what that yields us. So in this particular case, let me just copy this expression so that, or we have it in front of us. So mu plus minus will be zero. There are two expressions. One is for the positively charged ions and one is for the negatively charged ions. So what does the gradient of mu plus minus give us? So it will be, so the gradient of a constant will be zero. Then you have kBt. So then you have a gradient of the logarithm. So there will be 1 over c plus over c naught. Then there will be a gradient of c plus over c naught, or c plus minus over c naught, plus z plus minus ze gradient of the potential. So if we rearrange this, this has to be also equal to 0. So when we rearrange this, this C naught and this C naught cancels out, because this C naught can come out of the gradient because it's a constant. So we have KBT gradient of C plus over C plus, or C plus minus over C plus minus ZE times the gradient of the potential is equal to 0. And this tells us that the gradient of C plus minus over C plus minus is equal to minus plus. When this plus minus goes to the right hand side, this will become minus plus. It will be ZE over KT times the gradient of the potential. Now we must integrate this. So before integrating this, let us assume that we are working with a one-dimensional problem where you have a wall like this, and this can have some kind of charge to it, and let this axis be, let this particular coordinate, we can let it be x at the moment. It doesn't matter, none of this matters. So what do we have? So the gradient of C plus minus will then become dc plus minus over dx, and there's a 1 over C plus minus over here, and this will be minus plus ZE over KT, and this will be d phi dx. And because we are assuming that the walls are infinitely large, then the problem will solely depend on the x coordinate only. Meaning, if this is the y coordinate, the entire physics of the problem will be invariant along the y direction. So this will be invariant along the y direction. So what do we have? So when we integrate this, we will have log of C plus minus is equal to minus plus ZE phi over KBT plus some constant. We've just integrated this. It's a very simple integration. And what is the boundary condition for this particular ordinary differential equation? So the boundary condition is, as we go towards infinity, that is when x tends to infinity, the potential must vanish, because we've seen yesterday that as more and more charges screen the wall, the overall charge content of the region near the wall, including the wall, it will go to 0. It is almost like all the charge is being screened by the distribution. We saw that over here. So beyond this red control volume, all of the surface charge plus plus the double layer charges are screened. So we reach the bulk, and at the bulk, the concentration becomes equal to the bulk concentration, and the potential also becomes equal to 0. Okay, so this indicates that the concentration is the bulk concentration, and the potential becomes 0. And x tends to infinity has to be interpreted as a condition which is far from the wall. All right. So let us use that boundary condition. So ln C naught is equal to minus plus. So when phi equal to 0, this term will be 0 plus constant. So the constant is log C naught. So when we substitute this constant over here, we have log C plus minus minus log C naught is equal to minus plus ZD phi over KBT. In fact, if phi was not equal to 0, or it was equal to some bulk potential phi naught, we would have obtained somewhat the same result. So in case it was phi naught, we would have a log C naught is equal to minus plus ZD phi naught over KBT plus constant. So now if you substitute this constant, over here, we will have ln C plus minus is equal to minus plus ZD phi over kBt plus ln C naught minus, so plus minus Zd phi naught over kT, and this can be simplified as log C plus minus over C naught is equal to minus plus Zd over kBt phi minus phi naught. We've just taken this Zd by kt common, and we have made use of the fact that log A minus B is equal to, rather log A minus log B is equal to log of A over B. So this expression over here, it yields log of C plus minus over C naught is equal to minus plus Zd phi over kBt. Now let us work with this where the potential becomes zero. So when we simplify the blue expression, we have C plus minus is equal to C naught exponential of minus plus Zd phi over kBt. This particular expression is called as the Boltzmann distribution. This particular distribution is known as the Boltzmann distribution, and it does entail a bunch of different approximations that we have seen so far. But the most prominent approximation that I have not spoken about is that the ions, in whatever we have derived, the ions are considered to be point sized. This is very important. If the ions are not point sized, so I've drawn them as ions over here, but if they are point sized, they're literally not occupying any volume. So pushing another charge from infinity into this volume is much easier. So it's like you have, okay, let me give you that analogy as well. So suppose you have a number density of 5 number per say meter cubed, meaning you have 5 entities per meter cube. There's a cube, and there are 5 entities in this meter cube. Now imagine all of these 5 entities to be footballs. If they are all footballs, something like this. Now you want to push another football over here, then you will have more trouble than the case where you have the same number density, 5, but they are all marbles, or as we have discussed in the first, not discussed, as I have asked you, it's called kancha. Okay, so if we have 5 kanchas, then it is easy to put a kancha over here. It does not pose any significant difficulty. Okay, so with that in mind, we must appreciate the fact that the Boltzmann distribution automatically assumes that the ions are point sized, and there is a host of different things you must account for if the ions have finite size. And where do you think will the finite size become an issue? Yesterday, we did look at the number density. The number density with respect to the bulk concentration, we saw that the number density for counter ions, that is ions which have an opposite charge to that of the wall, the counter ion number density increases, whereas the co-ion concentration decreases. So for what distribution do you think that the assumption of point-sized ions will create a major issue?
For coans,
No, so for co-ions, the number density is reducing. So the number density reducing meaning you have less footballs. So you can put another football in that region. But the ionic density of the counter ions has increased. So already there are many footballs. So you will find it extremely difficult to push another football there. Does that make sense?
Okay.
All right. Now we have obtained what the Boltzmann distribution is, but this expression, what it does is, it doesn't tell us about the actual distributions. It does not tell us about the actual distributions. It only tells us that given a distribution of potential, okay, given a distribution of potential in the x, I mean x vector stands for given a spatial distribution of momentum, I would be then in a position to find out the distribution of ions. This is only the information we have. So we must find out yet another equation which will help us to find the distribution of potential. So the distribution of potential is obtained by means of the Gauss law, and we have discussed briefly upon this yesterday. So the Gauss law tells us that if we have a volume which holds a certain amount of free charges, then the electric field flux, the flux of the electric field over this entire volume, or the divergence of the electric field, the divergence of this electric field, right. So the flux over the area of the electric field is equal to the free charges inside the volume. Okay, this is what the basic Gauss law is, that literally you might have learned in electrostatics course in class 11. Now let me represent this free charges in terms of a volume integral. So it will be the charge density times dV. This is valid. Now I will make use of the Gauss divergence theorem to convert this area integral into a volume integral. So this will become the divergence of E over dV. Now because this statement is true for any arbitrary control volume, I can write this as the divergence of E is equal to the free charge. But what is E? Electric field is equal to minus of the gradient of potential. So I have forgotten to write this down in terms of the displacement. Okay. So the electric field is minus of the gradient of potential. So finally we have the gradient of, or rather the divergence of epsilon times minus of this is equal to the free charge. So epsilon is stands for the permittivity of the medium. Okay, how much the medium permits electric fields to be set up. So finally this expression, what does it yield? We need to find now an expression for the charge density in the domain. So because if epsilon is constant, so we get epsilon minus, or so this minus sign let us take on the left hand side or right hand side. So we have the Laplacian of phi is equal to minus rho f upon epsilon. Now if this particular box, it contains some positive ions and some negative ions, the question is, what is the charge density? The charge density. So if I were to only find out the density, it would be simply, the sum of C plus and C minus. What is the total density of this region? It would be the sum of these two densities. But in this particular case, we are more interested to find out the charge density, and so what can be the expression for the charge density? So we must obviously multiply it by its appropriate valency and the protonic charge. So it will be Z plus C plus E plus Z minus C minus E, and in case Z plus is equal to Z, Z plus equal to Z and Z minus is equal to minus Z, we can write this as Z E C plus minus C minus. So the charge density is how many more positive ions than you have than negative ions, and to top that we will multiply them with the valency and the charge. So the charge density expression therefore becomes minus Ze C plus minus C minus over epsilon. Now C plus and C minus we have already obtained in terms of the potential. So just to recall that expression, C plus minus equal to C naught exponential of minus plus Ze phi over kBt. So when we substitute this expression on the right hand side, we will have the Laplacian of phi is equal to minus Ze over epsilon. Now C plus is C naught exponential of minus Ze phi over kBt, minus C minus is C naught exponential of Ze phi over kBt. And so this turns out to be minus Ze C naught over epsilon e raised to minus Ze phi over kt minus e raised to Ze phi over kt. Let us take this negative sign inside. So once we take that negative sign inside, we get something like this. So if we divide everything by 2 and multiply everything by 2, this turns out to be 2 Ze C naught over epsilon. So what is this expression equal to? This expression is equal to,
Some hyperbolic function.
yes, so what hyperbolic? It is the sin h of Ze phi over kBt, because cos h x in general is e to the power x plus e to the power minus x over 2, and sin h of x is e to the power x minus e to the power minus x over 2. These are the two hyperbolic functions. I mean, there are more hyperbolic functions, but these two everyone should know. So thus we have converted into this. So, and because we are dealing with the distribution only in the x direction, what we can do is write down this Laplacian of phi as d2 phi dx2 is equal to 2 Ze C naught over epsilon times sin h Ze phi over kBt. Now the question is, this equation is nonlinear. It is nonlinear because of the presence of the sin h term, but despite being nonlinear, there does exist a solution for this uh, equation. But we will not worry so much with the nonlinearity. And actually, when can we not worry about the nonlinearity? And we'll deal with that. We'll discuss that also. You will see that for most of the commonly occurring, naturally occurring phenomena, you will see that you can actually linearize this equation. So we proceed with linearization of the equation. So this particular equation is called as the Poisson Boltzmann equation. So the Poisson Boltzmann equation is an equation which helps us to find out the distribution of potential in a medium in which there is a certain ion density. So after we linearize, so let us linearize. So linearization means sin h of Zd phi over kbt is equal to Zd phi over kbt. This is what linearization means. D2 phi dx2 is equal to 2 Zd c naught over epsilon times Zd phi over kbt. This becomes 2 z square e square c naught over epsilon kbt times phi. So we can write it like this.
Linearization is valid for small phi's only, or
Yes, I'll come to that. I have redistributed this. I have rewritten this equation in this particular form. So can you tell me what the unit of this term in the bracket should be? What should be the unit of the term inside the bracket?
meter?
Perfect. It should be meter squared, but yes, I think you got it because there's a del x2 over here. So the reason it has to be meter square because on the left hand side you have a second derivative of phi. So the unit on the numerator is both phi, but the unit on the denominator on the left hand side we have a meter squared. So obviously this entire thing has to have a unit of meter squared. So let us write it down as phi over lambda d squared. So the lambda d squared parameter is the square of the d by length. And we will come into the physical picture of the d by length in a while. It is the square of the d by length and it is epsilon kbt over 2 z square e square c naught. Alright, so how can we solve this equation? So we have the governing equation. We need two boundary conditions because it's second order differential equation. So obviously we need two boundary conditions. So what can be the two boundary conditions?
Phi at infinity is 0.
So phi at infinity is 0 and
And
the other condition is that the wall that at x equal to 0 we will specify some potential. Okay, so the other condition is this. There is no other consistent way of writing this. So the potential at the wall, it is called as zeta and it is called as the zeta potential. So throughout your study of microfluidics where you're dealing with electrokinetic flows or your analysis with batteries or in colloidal science, you will always encounter this parameter which is known as the zeta potential. So the zeta potential is what characterizes the surface. If the charge density at the surface, if the charge density at the surface is very high, if this charge density that we drew at the surface, if it is very high, then obviously the zeta potential will be very high. If it is very low, then the zeta potential will be very low. So we must solve this subjected to this. Before solving that, when can this be true? When can this approximation be true? So let me get out my calculator. Let me see if my calculator has the sin h function. If not, we will open MATLAB. But does it? Oh, we can simply do the exponential thing. Okay, so the idea is, I mean, there are various ways to do this also. So let me show you a very quick and dirty way. Let me open up my MATLAB so that I can create a plot and show it to you. We can actually make a plot of some parameter, say this is y, and we will plot z equal to y like this, and we will plot z equal to sin h of y, and we will see till what distance are they going to match. So if they match only till this distance, then we will say that when y is less than y threshold, then we can say that yes, you can approximate sin h y with y. Does that make sense?
Yes, sir.
So let me quickly plot it in MATLAB and show you. Takes a bit of time for MATLAB to load. Yeah, I have the plot. So okay, so what do you see over here? So the blue function is y equal to x, while the orange function is y equal to sin h of x. This is the x-axis. So we see that till -1 and 1, the error incurred in the approximation is not that high. This is within tolerable limits. But beyond this, it really diverges. Okay, beyond these values, it really y equal to x keeps going like this, but this sin h function blows up to infinity. Sort of. I mean, it doesn't blow up immediately, but because of the exponentials involved, you will suddenly have very large values. So, what is the value of sin h1? So, e to the power. So, let me go to my calculator. It's, or I can simply chug in the number in MATLAB, and one moment. Let me tell you the value of sin h1. Sin h1 is equal to 1.1752, whereas, so this value is 1.175, whereas the error, when you approximate it as 1, so you get a 17% error, and that's fine, that's not too bad. So this approximation is justified, when Ze phi over kBt. So this means that when Ze phi over kBt is less than 1, then our approximation is justified. But in the domain, the highest magnitude of voltage that we had seen, the highest magnitude of voltage is at the wall. Okay, so the electrical potential at the wall has the highest magnitude. Keeping in mind this fact, we have to ensure that Z is zeta over kBt has to be less than 1. The magnitude of this has to be less than 1, which means zeta has to be less than kBt over Zd. So the electric potential at the wall, if it is less than the entity kBt over Zd, then we can say that the approximation is justified. Now, what is the unit of kBt over Zd? What should be the units of kBt over Zd?
Same as zeta.
Yes, but so what is the unit of zeta? Zeta is the potential. It will be volts. Okay, so this is the zeta potential and this is called as the thermal potential, because it is sort of like the electric potential associated with the thermal vibrations of the ion. So we must ensure this so that zeta has to be less than kb into T over Zd. So now let us put in some numbers. So kb is 1.38 10 to the power minus 23. T is 300 Kelvin. Z is, you can assume it to be 1, and E is 1.6 10 to the power minus 19. So if we plug in these numbers, so we will find that the zeta potential, so let me put it 1.38 10 to the power minus 23 times 300 over 1.6. So it comes out to be 0.025875, meaning that the zeta potential at the wall has to be less than 25.8 millivolts. And you can approximate it as 25 millivolts. So the potential when it is less than 25 millivolts, you can easily justify the uh, linearization of this problem. So this is quite simple to solve as well. So we can simply write phi is equal to a e to the power exponential of x over lambda d plus b exponential of minus x over lambda d. Now, keeping in mind that phi at x tends to infinity is equal to 0. So at x tends to infinity, this term will naturally become 0, but this term will blow up. That is why this constant has to be 0. So phi is equal to b exponential of minus x over lambda d. Now we can simply make use of the potential at the wall. At phi at x equal to 0 is zeta. So zeta is equal to b exponential of 0, which is 1. So b is equal to zeta. So when we combine these two, we get phi over zeta is equal to exponential of minus of x over lambda d. Now this also helps us to interpret what this lambda d is. It is the distance, or it is like the measure of the distance after which the potential will become 1 over E times the potential. not the potential, but this potential at the wall, meaning zeta. Meaning when x equal to lambda d, when the distance from the wall is equal to lambda d, we will have phi over zeta is equal to exponential of -1, which implies phi is equal to zeta over e. So the value of the potential has decayed by a factor of 2.7. Okay, so it is like a measure of this distance that we had drawn. This, so if the potential over here is zeta, if the potential over here is zeta over e, so value of e is 2.71. So then we say that this this distance is called as the d by layer thickness, or the electrical double layer thickness. Okay, so the lambda d that we had defined, so this is called as the ideal thickness. The EDL stands for the electrical double layer. Okay, so it stands for the, so this is the ideal thickness squared actually. Okay, so now everything has become clear. So if the potential solution is this, e to the power minus x over lambda d, we can now substitute it in the solution for the concentration. So let us write down the solution. So phi is equal to zeta exponential of minus x over lambda d, c plus equal to c naught exponential of minus z5 over kt, c minus equal to c naught exponential of z5 over kt. So let me just quickly plot them in MATLAB to show you. So let me copy this image. So this is the decay of the potential. So I've set for this particular, for plotting this only, I have set zeta equal to 1. I have set the lambda d equal to 1, and I have set all this ZE over KT, all these things I have set to 1. So because they are just constants, I just need to know the functional dependency. Okay, so what's going on? So the potential is decaying like this, and wherever the potential becomes 1 over E, somewhere over here, so this is the thickness of the double layer. So the double layer thickness is the region. Remember this because it will be useful for electroosmosis. So the double layer thickness is the region where majority drop in electric potential occurs. And it occurs over here. Now what about these two? So this is the distribution of co-ions, that is the number density from this base value. So this is the bulk number density. So the number density is 1. So the co-ion concentration is low at the wall, whereas this is the counter ion number density, that is high near the wall. And when you have steric effects, meaning when the finite size effects do come into picture, this cannot go very high. So there will be some distribution like this. because you cannot push too many number densities in this small region. You have a certain threshold, meaning your volume can only hold so many footballs. So that is the logic. So this is how the counter ions are distributed, while this is how the co-ions are distributed. Okay, so let's take a 5 to 6 minute break, after which we will study about, or we will look into the aspects of electroosmosis based on whatever we have learned in the distribution of the electrical double layer. So we will look at electroosmosis and streaming potential, and that will be it from my end. So please hang around. I'll Let's just have a small drinks break. Alright, so let us continue our discussion. So now we will turn to the flow actuation by means of electroosmosis. So electroosmosis refers to the motion or relative motion of fluids due to application of an external electric field. Okay, it refers to the actuation due to an external electric field. And let us first draw the surface. So yes, you will have a microchannel. Microchannel will I've just drawn the cross section of a microchannel. And just a moment. And for this microchannel, suppose that the thickness of the microchannel is 50 micrometer. So now the question is whether electric fields can cause the motion of the fluid. So electric field is applied along the length of the channel. So before that, we must look at what the typical thickness of the electrical double layer is. Okay, so let us just copy this expression and crunch some numbers. So let me give you some typical values. So epsilon is the permittivity of water, which is almost 80 times the permittivity of free vacuum, which is 8.85 10 to the power minus 12. Kb is the Boltzmann constant, 1.38 10 to the power minus 23. T is 300, like room temperature. Z is 1. E is 1.6 10 to the power minus 19. And now what is C naught going to be? So C naught is the bulk concentration. So it is the bulk number density. That obviously depends on the molarity of the solution. So a salt solution like KCl, one can have a salt solution like 1 millimolar. So 1 millimolar means 10 to the power what? So it is 10 to the power minus 3 times the Avogadro number per liter, right? So Avogadro number is 6.023 10 to the power 23, and this many molecules lie in 1 liter solution, moles per liter. So we have to convert liter into meter cube. So there will be a 10 to the power minus 3 also. So this cancels out. So this turns out to be approximately 10 to the power 23. Okay, so the number density we can assume it to be 10 to the power 23. So let us quickly crunch these numbers. So epsilon is 80 times 8.85 E minus 12 into temperature into Boltzmann constant divided by 2 into z square into E square times C naught, which is 10 to the power 23. So this term comes out to be 5.7 10 to the power minus 16. So when we take a square root of this, we get 2.4 10 to the power minus 8 meters. So this is 24 nanometers. So we see that the distance over which the electrical double layer, the potential in the electrical double layer decays is only 20 nanometers. I mean, it obviously depends on the concentration, but it is not very large. So compared to 50 microns, 24 nanometers is very small. So if we consider the half channel height, so the half channel height is 25 micron. So it is 25 10 to the power minus 6 meter. If we compare this to the electrical double layer thickness, so let's say we take this as 25 nanometer. So it's 10 to the power 3, meaning 1000 times larger. So this half channel height is 1000 times larger than the potential that will be generated. So if I draw the potential like this, so the potential will vary only in a small distance, after which it will become equal to the bulk potential. Okay, so with that in mind, we have seen that the thickness is quite thin. So we have the wall. We will draw the wall, and now we can study what will happen when electric field is applied. So suppose the channel is negatively charged. Suppose that the entire channel is negatively charged. So for this negatively charged wall, what will happen? If the solution is KCl, then there will be a larger number density of positively charged ions in the vicinity, meaning that the up until the dBi layer, so this is lambda d, this region will have more positively charged ions than negatively charged ions. And what that means is the region near the wall does hold a net charge. But what about the region away from the wall? In the bulk, the number densities of the ions are equal because it decays beyond the double layer. So in the bulk, the number densities being equal, the number of ions, if they are equal, then there will be no charge. So this will have no charge. So when it is driven by an electric field, this region will experience a net force. So this region, it experiences net force. So when the electric field is like this and this region has a net positive charge, in which direction will the charges experience the force? It will experience a force in this direction. It is like having a positively charged ion and electric field is like this. So this will be pushed in this direction. Okay. So this is what drives the flow in the channels. Now let us try to quickly look at the mathematics of it. So the flows are devoid of any kind of inertia, and we will have the same equation that we had done for the Poisson equation. So this rho E is the charge density. And this particular term, this particular expression is equal to the charge density multiplied by the electric field. So this term is like the electrical body force. And this electrical body force acts in the direction of whatever sign rho E has, and it is in the direction of the electric field. So now, what is the simplification that we can do? So if we say that there is no pressure gradient applied, this particular term will vanish. So this we will set to 0 because we are not applying any kind of syringe pump or any kind of peristaltic pump to drive the flow. So no applied pressure gradient. So we have 0 equal to mu del 2 u del y2 plus rho e times e. Now we need to solve this. So this is the y direction, and what was rho? If we if we look at this expression, So from this expression we can write that rho is equal to minus epsilon Laplacian of phi, and if phi only varies in the y direction, this can be written as minus epsilon d2 phi dy 2. So rho is minus epsilon d2 phi dy 2. So let us write this over here. So I have written this as E vector, but this is not correct because we have written only the x momentum equation. And in the x momentum equation, we must only consider the electric field component in the x direction. So this is that component. Just a moment. All right. So yeah. So this will be d2 phi dy2. So now if we take this electric body force on the left hand side, or and we can rearrange, we can easily write mu d2u dy2 is equal to epsilon e d2 phi dy2. And now this equation is rather straightforward to solve. And what we will do over here is integrate this. So we have d2u dy2 is equal to epsilon e over mu d2 phi dy2. So let us integrate this once. We will obtain du dy is equal to epsilon e over mu d phi dy plus constant. Now, how to find out this particular constant? We can say that at the center line, at the particular center line, because of symmetry, du dy has to be 0. That is, the gradient of velocity along the y direction has to be 0. And also, because we are in the bulk, we can say that d phi dy will also be 0. And this d phi dy equal to 0 does not really depend on whether it is the bulk or not. It will be 0 purely via symmetry. So if that is the case, if du dy and d phi dy both become 0 at a common point, that is the center line, then that will naturally mean that this constant has to be 0. So we have du dy is equal to epsilon e over mu d phi dy, and when we integrate this one more time, we get u equal to epsilon e over mu times phi plus constant. Now how can we evaluate this? What kind of boundary condition can we apply here?
No slip at wall.
So we can apply the no slip boundary condition at the wall, where we can say that at y equal to 0, u equal to 0, and phi equal to
Zeta.
zeta. Very good. So when we apply this over here, we will have uh, 0 is equal to epsilon e zeta over mu plus constant. So therefore, u can be written as epsilon e over mu phi minus epsilon e over mu times zeta. Okay, so we have epsilon e zeta over mu times 1 minus, or rather minus epsilon zeta. So this will be 1 minus phi over zeta. So this particular velocity profile is called as the electrosmotic velocity profile. And this particular term, which has the units of velocity, is called as the Helmholtz Smolukowski velocity. Okay, and if you look at uh, how this why this velocity is important, if you look at why this velocity is important, we can write u is equal to, so if I call this as UHS, then we can write this as UHS 1 minus phi over zeta. So when phi goes to 0, that is we are uh, beyond the electrical double layer, then u will become equal to UHS. So fine, u will become u equal to UHS, meaning at the, suppose this is the edge of the electrical double layer, the velocity will become UHS over here, then it will stay constant and it will again go to 0. So here there is no slip boundary condition, but at the edge of the electrical double layer, we have a velocity, and this velocity will sustain over the entirety of the length. So this velocity is called as the Helmholtz-Smolukowski velocity, and because this thickness is so small, it is 1,000 times smaller than the channel half height. What it naturally means is, if you were to study the dynamics over 50 micrometers, it will almost appear that this Helmholtz-Smolukowski velocity is occurring at the wall. So this Helmholtz-Smolukowski velocity is effectively like this slip velocity. Okay, so in order for solving many problems of electroosmosis, we can often assume that the velocity is also equal to the slip velocity instead of solving for the entire double layer. Okay, so let me
And
just,
the velocity profile is solely because of the electric field that is
yes,
uh,
there is no additional pressure
not
gradient.
traditional. Okay.
So the external of this particular course is asking for me for the link. So let me just quickly send him the link. There is one delegated. One moment. He has to have the link, otherwise he will not be able to evaluate us, evaluate these sessions. Just give me a moment. Okay. All right. So let's continue. Yeah. So this was all about electroosmosis. Now let us look at a very useful thing that happens. So suppose now, instead of the charged particle, we have a glass particle. So this glass particle will acquire some charges because of the physical interactions with the surface of the glass and the electrolyte. So now this glass particle, because it will become positively charged, and this kind of charging does happen, and the area of colloidal science does deal with why this kind of charging takes place. So this is solely because of surface adsorption or some site substitution. But what matters to us is, because this glass particle has become positively charged, it will attract negatively charged ions from the solution. It will attract negatively charged ions from the solution, and the region in the vicinity of this charged sphere, it will have a net negative charge. So now when you apply electric field like this, now because this is negatively charged, the negatively charged cloud will be pulled in this direction. But if the negatively charged cloud is pulled in this direction, if the fluid wants to come here, by Newton's third law, the particle has to go here. And this kind of mechanism, it is also there in electroosmosis. Okay, so this, or rather, electrophoresis. So this is broadly what happens when you have electrolytic solutions and in the presence of electric fields. Now let's go to streaming potential. Okay, so streaming potential means you have a channel like this, but you do not apply any electric field. The electric field is not applied, but there is a pressure gradient which drives the flow. Now, we have all seen that regardless of whether the flow is driven by a pressure gradient or electric field, there is some net charges at the wall. There is a distribution of net charge at the wall, and if the walls are positively charged, or let's say that the walls are negatively charged, let's say that the walls are negatively charged. So what will happen is, because of the pressure driven flow, these negatively charged, rather the positive clouds, so cloud this cloud, they are positively charged, whereas this region has no charge. So when there is a flow in this direction, the cloud is taking a flow like this, so you have a net positive charge accumulation on the right hand side. So if there is a reservoir over here, if there is a reservoir over here, then you are causing the positively charged ions to be advected towards this side. So there will be a larger accumulation of positively charged ions over here, and that will cause an electric field to act like this. Now remember that these clouds are also positively charged. These clouds are also positively charged. So because of the electric field that has been now induced because of the accumulation of the charges on the right hand side, what will happen is the clouds will experience a force in the opposite direction to that of the pressure driven flow. Okay, so the pressure driven flow wants to make the flow go in this direction, but the electric field wants to make the flow go in this direction. But here the electric field is not applied, it is induced. So this electric field is created by a potential which is called as the streaming potential. So the streaming potential term itself conveys that it is the potential which is set up by the streaming of the ions from one end to another. So it is very much like the Lenz's law that we have studied in electromagnetism, where the cause of the flow, that is the pressure gradient, is sort of being uh, adversely affected. The cause of the flow is repelled by the electric field that has been induced by the flow itself. Okay, this is very much like analogous to the Lenz's law that you have studied. So this particular phenomenon is called as streaming potential. So the mathematics of this, it's got involved, it does require a bit of fluid mechanics background, but overall we have looked today at all the mechanisms, all the fundamental aspects of the electrical double layer and why these electrokinetic phenomena takes place. And at the heart of all this phenomena is the electrical double layer, which is a net charge layer in the vicinity of the wall. Okay, so we have covered a lot of basic ideas. We've looked at various plots, and yeah, so that's it from me for this particular session. Uh, Let me stop sharing and let me stop recording.